I'd like to thank you for the invitation and the opportunity to talk here. I have to admit that in deciding what to talk about, I wasn't very sure about the audience. So I saw quite a bit of, I saw the talk by Randy, essentially about conservation laws and fluids, and I said, well, we're going to talk about, I let you know a little bit more about the beauty of solids, okay? Or what are the challenging problems in solid mechanics that we have. So maybe my talk will not be so geared to very large-scale applications, but more on highlighting some challenges and solutions to some of them that we encountered. So let me start by acknowledging my collaborators here. I'd like to, so first of all, I have here Alex Tenaik, who is a student at Stanford with me, Kedar Gadjanankel, who's another student who did the work on parallel asynchronous variational integrators I'm going to show. Deborah Sulski from University of New Mexico, and Patricio Neff from Germany, whom I worked with on discontinuous Galerkin methods for linear elasticity. Michael Ortiz and Jerry Marsden from Caltech, together with Matthew West at Stanford now, also an assistant professor. We work together on variational integration. And finally, Emily Carter from Princeton and Kai Kaspersen at Lawrence Livermore National Labs, whom I work with on phase transition in irons, which I'm going to show. So at Stanford, soon ago, we were awarded one of the 4 national centers for biocomputation by the National Institute of Health. So this is called SynBIOS, and our focus is on the physics-based simulation of biological structures. So 2 of the key challenges we have are the construction of a virtual aorta and a virtual muscle. And the 2 requirements that we like to have are that they should be patient-specific, and they should be able to model both healthy and diseased tissue. So this type of models would be used eventually, for instance, for the simulation or the study of a procedure of stent implantation on an occluded artery. In this procedure, you insert a stent into the artery where the occlusion is, you inflate it with a balloon, you compress the plaque or the calcified tissue that is occluding your circulation, and you leave the stent there that will prevent the artery from compressing back again. In doing that, you deform an initially very compressed artery into a largely deformed shape. So when you do that, you go well beyond the range of nonlinearities in the material. You need to account for the large changes in shape that you have and for the large changes, if you want, to give you a pictorial image, in the distance between atoms or the arrangements between atoms that will change the constitutive behavior or the stress-strain response that you will measure. Muscle presents similar challenges. And one way to go about this right now that will make possibly a big difference on that is in taking advantage of a wealth of information that is being now available through imaging techniques. Like, for instance, using confocal images of a piece of tissue on the rat aorta, where each color here indicates the different type of organisms or structures in the tissue that you have. So ideally, we would like to build image-informed models of the material behavior that will be accurate enough to distinguish between healthy and diseased tissue. So I'm not going to talk about this problem because we haven't solved it yet, but this is the type of challenges we have in trying to model materials that undergo large deformations. Nonlinearities play a strong role. A second area where highly deformable materials are everywhere present is in homeland security applications. When you're trying to design a shield or a structure that will withstand strong loads, such as impacts or explosive loads. So in this case, your casing, for instance, that is containing an explosion advancing inside the casing, will probably fail and it may fail by either cracking, for instance, this is a nonlinear material behavior, or by localizing the formation on a very narrow region. This is called a shear band. In any of these cases, you don't know where the failure will occur. You don't know where your solution will become highly localized, okay? So you need to somehow devise a method that will allow you to capture such a set without knowing that a priori and keep the computational cost still low. This problem has not been solved yet, okay? But let me explain you a little bit more on what are the underlying, at least one of the underlying effects of nonlinearities in the material behavior. So, for instance, you can go to a laboratory, make a probe like this, made of the material that you want, you pull it from both ends, and you measure the force as a function of the distance that you are that the machine has traveled with the probe. So if you were to measure a material, a linear elastic material, you will see a straight line here, okay? A nonlinear elastic material, and this is called a material nonlinearity, just because the atoms are being pushed away from each other, will have a different curve. So if you map this back into your highly localized deformation, you would see that probably the atoms around here are in this part of the curve. But the atoms just on the failure line will be on this part of the curve. That means that if you push your material a little bit farther in the formation, any little bit of stress that you want to get or force that you want to get out of your material in this area will deform your material a lot more. And that's why the deformation localizes there. So in dealing with solid mechanics problems in large deformations, you need to be able to somehow capture these nonlinear effects. And I have more examples later on. So, as I said, I'm not going to talk about how to solve localization problems, which still there are a lot of methods, but there are still some open issues there, very important issues. But I'm just going to say, I'm going to discuss three methods that are relevant for the simulation of highly deformable materials. If you want to simulate one of these things, you need to discretize in space. You need to say what the material constitutive behavior is, what the stress-strain relation will be, and you need to be able to integrate it in time, at least, okay? So I'm going to talk about a new method for solving nonlinear elasticity equations in a quasi-static regime, which is using discontinuous Galerkin methods. And I'll explain why. This is work together with Alex, and he has a poster outside. Then I'm going to talk about an example in which we construct the material response under large deformations from quantum mechanics. We do it very accurately, and we are able to capture what happens when the material, when you really pull it, when you really push it. Okay? So this is the joint work with, this is on phase transformations in iron, and this is joint work with Kyle Kaspersen and Emmy Carter and Michael Ortiz. And finally, I'm going to talk about time integration, and here I'm going to show a set of time integrators that essentially allow each element in a finite element mesh to have its own time step, and in addition to that, you have very nice underlying geometric structure that gives you very nice conservation properties. I'm going to try to describe that. I'm going to include also the latest version of this, which is the parallel version, which it's being finished by my student Kedar Kale. So the first part is discontinuous Galerkin methods for quasi-static nonlinear elasticity. So many of you may not be familiar with the nonlinear elasticity problem, so here is a crash course. The idea is the following. You start with a body that is in a reference configuration B0, and you want to describe how the body will deform through a deformation mapping. We call it a deformation mapping that maps each point here to another point where the body, where that particle of the body will end up being. Okay? So this mapping is called the deformation mapping, as I said, and many of you may be more familiar with displacements, which is from linear elasticity, which is just the vector that joins the original position of the point, where the point is at the deformed configuration. So associated with So the problem of nonlinear elasticity is to try to find the stationary points of this functional, which is just the potential energy functional, and it's just the integral over the entire body of the elastic energy of the material evaluated at the gradient of your deformation mapping. So this gradient of your deformation mapping is telling you how close points in your material are separating. Okay? So you construct, depending on how much they separate, you construct a function. This is called the strain energy density function that tells you how much energy you need in order to pull them apart. If you take the derivative of this, of W with respect to this 3×3 tensor, the gradient of a vector, you get what's called the stress tensor. And this is highly nonlinear, and we will see some of those effects later on. So why do we want to use discontinuous Galerkin here? First of all, let me tell you what discontinuous Galerkin is. So discontinuous Galerkin is just a finite element method with a space of discontinuous functions across elements. So that means that if you have a field and you're using a conforming or continuous finite element space, you have this type of mesh formed with two triangles, you have two elements, and you have 4 degrees of freedom. And functions, any function in your space is continuous at that interface. In this continuous Galerkin, these two same elements you will allow discontinuities to appear across the boundary, and hence you will need 2 more degrees of freedom. So for this mesh, you're going to have 2 elements, but 6 nodes. So when you compare meshes in discontinuous Galerkin and in conforming methods, you're really comparing meshes with different number of nodes. Okay? So the reason to explore this continuous Galerkin method is that they've been proved to be very excellent or very good for conservation laws. That's another perspective from finite volumes perspective, probably. But that's true. A lot of they've been really welcome on that arena. And the question is, why don't we have them for elliptic problems? And there have been some attempts. For instance, the first of all was the interior penalty method by Doug Arnold. And the problem that has hampered this effort has always been that it's very hard to find values for stabilization parameters for these formulations that you need to add. And it's also it has never been proved to be advantageous to have more degrees of freedom to compute the same solution. So I will prove that those 2 arguments wrong in this talk, okay? So any discontinuous Galerkin method is based in essentially one observation. The idea is the following. In DG method, a function and all its derivatives are individually approximated. And the relation between the function and the derivative is inputted in by design. That's how you design your method, okay? And why do we do that? Because if this is your function, these are your elements. And this is, for instance, the piecewise discontinuous functions that you are using to approximate it. Then when you take the derivative of this function, at the interfaces, you'll have a bunch of delta functions. You'll have a generalized function. And we need a real function to evaluate there. So what you do is you somehow build a projection of this function, of this generalized function into some new space or discrete space to interpolate your derivatives, okay? The problem that we have here is that if you initially had 3 degrees of freedom per node to describe the motion of each node in space, now if you have to keep also track of all the components of a 3×3 tensor, second order tensor, you have now 11 degrees of freedom per node. So suddenly your degrees of freedom have the size of your problem has exploded. That's a really tough benchmark to beat, okay? So we found a way, which is really the way we are advocating, and it has been used occasionally, but not adopted by the community, to just regard this design of the derivative as a linear operator, DDG, on the discrete, on your discrete functional space for your field. That linear operator is local. That means that you can compute it with the information that you have in one element and maybe some of the surrounding elements. Okay? So in the end, what you end up having is only one field, and you can formulate your problem with only one field and keep the number of unknowns under control. Okay? So if you want to know more about how you define this operator, I invite you to go and see the poster by Alex. So this is the design of the method. We want to find stationary points in the discrete space that we constructed of this functional, which is just the potential energy of the system, but now evaluated with what we call the dg derivative of the deformation mapping. It's simple as that. So then, when you vary this to find the conditions for the stationarity of this functional, you get the Euler-Lagrange equations, and this is the set of nonlinear equations that you have to solve to find the deformation of your material or of your body. So let me show you how this works. So this is a simulation of a cylinder where we clamped it from the bottom. This is three-dimensional. We have piecewise linear elements, and we are pushing it from the top. So the contour plots that you see, whenever you see contour plots, that means that there are discontinuities across those elements. So discontinuities, in fact, appear in the solution. It's not, inside your functional space, you have the possibility of having a continuous solution. However, you minimize the energy further, you minimize your potential further if you include discontinuities across the elements. So what's the advantage of this? Well, let me show you this. This is an example I really, really like, because this shows that DG has quite a bit of an advantage over other formulations. So here we have a block that will be compressed from the top using discontinuous Galerkin and piecewise linear conforming finite element methods. Okay? So this is the standard. This is what everybody in the industry uses. Okay? So let me show you how it goes. So you expect the solution to be symmetric. You're not breaking the symmetry anywhere here. And that's what happens in DG. You're taking advantage of the fact that you have discontinuities to accommodate this deformation. And you'll never get the right solution with the conforming finite element formulation. No matter how many times you refine your mesh. You can take a mesh as fine as you want. That is just a subdivision of this one. You will never converge. This is, of course, an effect of the nonlinearity. It's fully an effect of the nonlinearity. But you can argue, okay, what's the meaning of element superposing? Well, I can tell you, I can give a meaning to this. Okay, I can project this shape if I needed to understand, if I wanted to have a single-valued deformation mapping at each point. Okay, then another example where this formulation has a lot of several advantages. So one problem with that has been pervasive in this type of in elasticity and sometimes in fluids as well was always to deal with kinematic constraints. For instance, incompressibility. Okay, here in nonlinear elasticity, incompressibility is even worse than, for instance, in fluid mechanics, because you have a nonlinear constraint that you have to satisfy at every point in your mesh. Okay, so what happens is that if you want to use low-order elements like piecewise linear everywhere, your solution locks, and I will say what that is soon. So people have formulated methods using MITS methods in which you introduce Lagrange multipliers and hence increase the size of your problem substantially, or for instance using penalty method that you never know what the right penalty value is, and it may not be unique in the entire domain. So how does DG behave? So let me show you what happens when you do this with conforming finite elements. So we are pushing this cylinder from inside. Okay, we are imposing a displacement. This is an incompressible cylinder. And we are measuring what the traction, what force we have to do on the interior surface is. So this is the traction as a function of how much we change the interior surface of the cylinder. So note that we go all the way up to 10%. So this is large deformations, okay? So these solutions in square blocks or crosses are the ones from a conforming finite element formulation. And as you increase, and as you become more and more incompressible, the traction blows up. Okay? It increases unboundedly. However, for the same case with discontinuous Galerkin, as you increase and you get more and more incompressible, the traction stays the same. Okay? We did not add any more degrees of freedom. We did not have to choose a penalty parameter. Okay? So this is very, very promising in that sense. And it's still very cheap. These are piecewise linear elements. So the final observation I want to make is that, you know, as I said before, people have been, the standard or the common knowledge was that when you use discontinuous Galerkin, you had to pay a lot more computational cost for the same accuracy. And so we just went ahead hoping to have very bad results and plotted the total number of degrees of freedom as the displacement, the L2 norm of the displacement error that we had as a function of the total number of degrees of freedom for a solution that is displayed around here. So we have here the curve for conforming finite elements, and in green the curve for DG, for discontinuous Galerkin methods. So what's surprising here is for the same number of degrees of freedom, both are equally accurate or nearly equally accurate. And remember again, as I said before, when you say 100 degrees of freedom, you're comparing a coarser discontinuous Galerkin mesh with a finer conforming mesh. So you're really using the discontinuities here.
Question.
Yeah.
So just, I'm a little confused about the counting. If I had a triangle mesh, and I let every vertex be an individual degree of freedom, then in general I would expect 6.
Yeah,
Factor 6, and for tets approximately 15 or something.
exactly. So okay, so this is not as such a paradise as I'm describing it. Sometimes things go bad, and go bad in this sense. Sometimes sometimes the linearization of your discrete functional loses positive definiteness, even though the continuous problem may not lose it at that point. So this is like a numerical buckling, a numerical loss of stability. So you need to add some stabilization, and this is the type of stabilization that we add. This is standard in discontinuous Galerkin, and this is the effect of stabilization. We're considering here a problem in which we are loading a material with 1,000 steps, and at each step we are plotting the minimum eigenvalue of the linear form. We are plotting the minimum eigenvalue of the matrix that we use to solve each one of the linear systems associated with the Newton-Raphson iteration. So if we don't add enough stabilization, at some point we lose, we get a singular matrix. Okay? So this is the numerical buckling. However, with enough stabilization, we are able to travel through the formation well enough. So we prove a theorem about this. I'm not going to go into the details of this, but essentially what we say is that if the shape of your material is right, and some parameters associated with the constitutive relation of your material are right, so some conditions are satisfied, then you can add a stabilization parameter that is estimated from below with a formula like this. Okay? So now we have a formula to estimate the stabilization parameter. Okay? Can be very expensive to compute. We are working on that, and we have some very nice results on that right now. But this can be computed. It's not just for beta large enough, it's for a given amount of beta greater than this that is given by this formula. So what's the effect of the convergence of stabilization on the convergence rate? So if we see the stabilization again, what we are doing here, this indicates the jump of the deformation mapping across two elements. So what we are doing here, we are penalizing the discontinuities across boundaries. So if beta is large enough, you're going to have a continuous solution. It will dominate your problem. So, of course, you don't want beta to be large enough because then your efficiency will suffer, okay? And this is the way it suffers. So again, we have displacement error as a function of the total number of degrees of freedom, and if we choose beta, we optimize beta, then you get discontinuous Galerkin to be more efficient than the conforming method, which is in this line in red. However, if you choose very large beta, then you're losing some efficiency because your solution becomes more continuous, and it's more like using a conforming mesh. Okay, so now we are using this. Yes.
Isn't kind of the upper limit, the upper, when you make theta very large, why isn't it just exactly like the conforming?
It is. Well, I mean, it's not. The solution will be exactly as the conforming mesh if you can solve it. Okay, because it will be really ill-conditioned. Let me put it this way. It will be very stiff. Yes.
On the graph, is the DG method, is that with or without the stabilizer addition?
This one?
Yes.
This one is with stabilization. That's what I'm saying, exactly. Okay.
When you stabilize, are you not effectively shifting where the stationary point is because you have an extra force term effectively?
No, I mean, the convergence will not be affected because, okay, this is the reasoning behind it. You're really looking for an H2 solution, if you want, or H1 solution. So in the end, you may the solution that you have will be continuous essentially. Let me say, depending on what dimension you are. So that term is 0 at the exact solution. So we are using now this to, I mean, we have a simulation here, but this is very crude. We hope to improve this. This is very preliminary, just to show that the method works, of a stent pushing against a region of plaque and a blood vessel wall where we just assigned, out of the shelf parameters, material parameters for these materials. I mean, we hope to improve this with image-informed models at some point in the future. So let me now talk about how this later point, which is how do we get constitutive relations? How do we compute with the computer the stress-strain relation? So the most often or traditionally used method has been to take a phenomenological approach. You take your sample, you go to the lab, you measure whatever you can measure. Remember that we have to measure here in a very long range of deformations, and this deformation path could be very different depending on your material. And you use that in your finite element simulation. So now what I'm going to show you is how we construct the strain energy density for one type of materials. These are materials capable of undergoing martensitic transformations. I'm going to tell a little bit what those are. So this is the problem. Iron is under normal temperature and pressure conditions a BCC lattice. That is, the atoms are arranged in this way. A cube with an atom in the center. If you hit it really hard on one side, you'll have a shock in the middle. And behind the shock, you are going to see some HCP. So the atoms would move a little bit. That's why it's martensitic, and would acquire this type of symmetry or arrangement. In fact, it will not be pure HCP, but it will be a mixture, something like this. This is not iron. This is another very beautiful material. What you are going to have there is very messy. But it will have some sort of segregation into what we call laminates or parallel plates of the two phases, some BCC and some HCP. So this probably is one of the most widely measured phase transformations in the history. So the national labs, for obvious reasons, for casing of weapons and things like that, have been measuring this for 50 years now. And surprisingly, there are no two measurements that give you the same value for the pressure at which the transformation occurs. Okay? So if this is the temperature as a function of pressure, or the TP diagram of the phase diagram of iron. So originally, when you are at low pressure and low temperature, you are at BCC. And if you increase the pressure suddenly, you go to HCP. Okay? Now, this point is not clear what it is. So what I'm going to show you is that based on the computations that we have, there is a reason why it's not clear, because this pressure is very sensitive to very small changes in the type of loading that you have. Okay, and we're going to do that building the best model of iron ever yet done. And the way to do that is to use what we call a multi-scale modeling paradigm. The idea here is the following. You look at your phenomena. This is heuristics, and people talk a lot about this a lot. But sometimes you can get a good method out of it. Okay, and a lot of people are looking into that, including myself. So you look at your phenomena as a hierarchy of different length and time scales. And at each length and time scale, you're going to have different physics, probably different relevant phenomena governing the behavior of your material. So for instance, at this level, quantum mechanics will govern. Okay? And at this level, which is like a micron-sized sample, you will have the laws of mechanics governing. Okay? Nonlinear elasticity. And the behavior of this 1 micron sample will be crucial to determine whether this structure will in the end fail. Okay? So what we're going to focus now on is on these two parts. In fact, given the audience, I'm only going to focus on this part. I'm going to tell you a little bit about this one. So what we did is building our strain energy density, W of F, using quantum mechanics computation. Okay? And we use that to solve nonlinear elasticity problems, to find the type of microstructure that the material forms when you load it. Okay? So these are the computations, the quantum mechanical computations. So density functional theory is the theory we used. So for those of you who are not familiar, density functional theory is an approximation to quantum mechanics in which you solve for the energy that a given atomic arrangement has, because atoms are bonded together. So as you move the atoms a little bit, you pull them apart a little bit, that energy will change. And that change of energy, you have to pay it with force, with stress. Okay? So you can do these computations. These were done by Emily Carter and Kai Kaspersen, and these are the results. This is the energy of a single cell of iron as a function of the volume of the cell when that cell is BCC, HCP, and here we have another phase as well, okay? And here you have the pressure as a function of the volume for that cell. And we also compute the elastic moduli and a lot of other parameters. The important thing about this is that we spent 2 months doing these computations, okay? We essentially computed, I don't know how many points there are here, but the quality that they have is that if you come here and you say, I want to compute another point at this position, you will just get the value that you interpolate from the other two. So it makes no sense to keep on computing. Okay? So that's why I say that this is the best model of iron ever. Okay? And now we have this in a table. It's you can access it and use it. And we use this to construct our strain energy function, elastic energy function, and I will tell you what feature that energy function has. But before telling you that, let me tell you how we compute the microstructure. The general problems of computation of microstructure can be stated as follows. If you have a microscopic sample, what is the microstructure that minimizes the elastic energy of the material for given deformations of the boundary? And in general, from homogenization theory, you can restrict yourself to consider deformations of the boundary that are affine. Okay? So if this is your sample that has 1 micron in size, okay, you impose on your boundary a deformation of the type f times x, where f is a 3×3 matrix or second order tensor, times the position x, where x is the position of a point in the boundary. So you deform it to something like this. Okay? So you impose that deformation on the boundary, and you wonder what is the deformation phi that minimizes the elastic energy that you generate inside. It's the same problem we solved before, but with the specific deformation on the boundary. So in general, you can check that a uniform deformation, this is called f times x, is a solution of this problem. I mean, it satisfies the Euler-Lagrange equation. It satisfies the stationarity conditions. But it may not be the only one. And when it's not the only one, it's that you get microstructure. So this is exactly this is a very nice example of what happens. So consider a fluid that can take two phases. Okay. So the defining characteristic of a fluid is that its elastic energy depends only on the changes of volume that you have. So this is the elastic energy of the fluid as a function of the volume, of the specific volume of your fluid. And you can have two phases, phase green and phase blue. So now if you have a container of the fluid and you change the size of the container, you push the container, I ask you, okay, and let's say that the specific volume of the fluid ends up being around here. I ask you, what's the phase in which you are going to find the fluid? So you say, okay, I have to minimize energy. I will come here. I see phase 1. I see phase 2. I see phase 1 has, or green phase has lower energy than blue phase. Oh, it's going to be in green phase. Okay? That's the uniform deformation. And that's not what nature does. So what nature does is it realizes that if you come here and you mix a little bit of phase 1 and a little bit of phase 2, so in your container you'll have now parts of fluid in phase 1, parts of fluid in phase 2, such that on average the volume is the same, so you satisfy your boundary condition, but the total energy of your system will be lower. Okay? So this is an effect of the non-convexity of your elastic energy function. And that happens in materials, and that's what happens. That's why we get all these laminated microstructures that I showed you at the beginning. And that's the nature of the elastic energy density that we build. We build an elastic energy density from quantum mechanics that is non-convex. It has all sorts of these type of wells. So once you have this elastic energy density, you say, okay, now I know what to do. I just go, I plug in my finite element simulation package, I discretize my microscopic sample, and I try to solve it with discontinuous Galerkin, with whatever method you want. Well, if you do that, this problem, you'll get a solution that you may not understand what it means. Okay? It will probably mix regions of, it will essentially oscillate from element to element, probably. This is because the elastic energy, because sometimes there are no minimizers of this problem that are actual functions. Sometimes you get a measure as a minimizer of this problem. You have to enlarge the space in which you seek for solutions. So an alternative strategy is to build a different finite element space. A finite element space that is informed on about the microstructure that your material wants to form. So this is the space of sequential laminates. And this is what we built. Okay? Let me explain you. So we would like to build a deformation of, for instance, a block like this one that has constant deformation gradient. The gradient of phi is constant on each one of these regions. Okay, this is called a laminate. So this the gradient of this deformation will be denoted here f plus and here f minus, and they will be in a relation lambda and 1 minus lambda in width or mass fraction. So since we want to satisfy the boundary conditions that we apply, the affine mapping on the boundary, we request this f plus and f minus with the lambda to satisfy to be equal on average. Okay? And at the same time, we don't want to generate cracks or dislocations between two parts of our material. So we have to satisfy another condition called the Hadamard compatibility condition that says that just the difference between these two tensors has to be a rank 1 tensor. So if you do that, okay, so that's a rank 1 laminate, okay? Then you can imagine that you can take the region F plus and generate a laminate inside that laminate, okay? That's a rank 2 laminate. And recursively, you can build any laminate you want. So we do that, and we try to minimize now the energy of the sample among all possible laminates. And there is an algorithm to do that that has been published. The reference is here. And that's how we find our deformed microstructure. So let me show you the results. Now, so here we have a BCC sample, which is in blue. And we we start with the deformation, and a fine deformation of the boundary, which is the identity, no stress. And we push it such that we compress, uniformly compress it, and add some terms that will distort it, okay? And we change the value of f12 in these resimulations, okay? So here we have f12 equal to 0.02, 0.03, and 0.04, very little. So you start loading, you go from f to f final linearly, okay? You just interpolate these two things linearly. And you know, as you go, you load, and at some point here, boom, HCP appears, okay? Here you have a mixture of BCC and HCP. This minimizes the energy. And then you go further, and you get a rank 2 laminate, a mixture of HCP and HCP with different orientations. If you do that, increasing the value of f12, this transformation appears earlier, okay? And you end up having a very complex microstructure in the end, a rank 4 laminate in this case. So back to the question I posed at the beginning was, what was the dependence of pressure on, for instance, a small parameter? Here it is. If you had no f12, you just have a uniform compression of your body. This is the black curve. You see a very nice, very smooth pressure as a function of volume curve. Now, if you add, for instance, 0.02, if you have f12 equals 0.02, a little bit of this distortion. This is the pink curve. You go smoothly, and here, boom, you transform. This is 25 gigapascals, okay? You keep on increasing, you get to 0.06. This is the red curve, and you transform at 13 gigapascals, okay? You keep on going, you transform again, a rank 2 laminate, okay? But, so you see that with very little distortion, you change the value of the onset pressure tremendously. And that's the explanation for the widespread, the spreading of measurements that people have. And one thing to notice here is that we did not use an experiment here to compute that the pressures, the transition pressures, were 13 gigapascals, which is what people measure. Okay? So we did this entirely with the computer. Yeah.
So with the computational realization, how do you make sure that you don't have numerical artifacts due to, let's say, mesh alignment, or, I mean,
no, there is no mesh alignment, because we build these microstructures. That's what I'm telling you. There is no finite mesh. We build, we parameterize, if you want, these sequential laminates, and optimize in that space of sequential laminates.
Yeah, but don't you effectively have to pick some directions in this space? Or?
No, well, you optimize in the direction. So you have to optimize over the normal. Yeah, yeah. Yes?
So you're taking the lamination convex out of the energy?
No, not really. It's very hard to say that. We try to, but we cannot.
Oh, but for a finite number of them, so you say.
Yeah, you try as much as you can to find a stationary point inside the set of laminates.
Yes, but not even the lamination convex out, the quasi-convex out.
No, of course. I mean, that's true. And, we can have a long discussion about whether quasi-convexity is the appropriate thing to request. So if you want to discuss about it, we can. I advise you to do that later. It's a long discussion. Okay. Finally, I would like to conclude this talk by telling you a little bit about time integration and variation and time integrators. So in particular, I'm going to talk about asynchronous variational integrators. This is just a class of integrators that you can generate within this theory. And the distinguishing feature is that you can integrate a mechanical system with different timescales depending on how stiff each one of the mechanisms inside your systems are. Okay, so that's the first feature. And the second feature is that the algorithms are derived from a variational principle. And as I said before, this gives you a number of very nice geometrical properties, such as a discrete Noether theorem, which guarantees you, by construction, not by enforcing it, by construction of the algorithm, that you're going to automatically satisfy, for instance, a conservation of linear angular momentum. And because of of the variational structure, you can also guarantee that the algorithms are going to be symplectic. And hence, you can apply, for instance, some of the backward theorem analysis, backward error analysis theorems. So, for instance, if you use finite elements, these asynchronous integrators allow each element to progress with its own time step, asynchronous, a little bit in the spirit of subcycling or element by element algorithms pioneered by a number of people listed here. However, we don't define regions of time steps. We just have a different time step defined locally for each element. And in molecular dynamics, similar ideas are embedded in multi-time steps, such as S-bar or impulse. So let me, before I tell you about the theory, let me give you some examples. This is an example in this dynamics where we simulate the rotation of the blades of an Apache AH64 helicopter. This is done with tetrahedral final element. This is done with. Oh, okay, I'm sorry. Thank you. So we simulate here the dynamics of the blade of an Apache AH64 helicopter using tetrahedral finite elements with 10 nodes. These are quadratic, within piecewise quadratic inside each element. And we choose the time step of each element using a Courant-Friedrich-Lux condition, CFL condition. Okay? So let me show you first what happens when the blade is really stiff. Okay? So here we have two views of the blade. One that is vertical, the other one that is horizontal. What's interesting is that, for instance, if you keep an eye on the center of the blade, it always stays in the same place. And the blade always rotates in the same plane. This is just a consequence of the fact that you're conserving linear and angular momentum exactly. Okay? So you see that in the rotation of this blade. Well, but this case is kind of boring because it's too rigid. So we just soften the material. We want to do large deformations now. This is not a realistic thing. You will not fly with this. But, you know, it's nice to see if it ever does it. Hold on. So how this flying spaghetti is rotating, but still you preserve the center, the location of the center of your blade, and you rotate always in the same plane. And you will see that the energy is perfectly well preserved as well. So this is not unstable numerically, it's just mechanically unstable, if you want. So this is the key advantage of using asynchronous algorithms, the fact that you can save computational cost by doing less computation where you don't need it. So the CFL condition tells you that in the small elements you will have to take smaller time steps. So here I plot the logarithm of the number of updates that you need to do on each element after the blade has done 150 revolutions. So here is a zoom out of that region, so you see that the center has done a lot more updates than the ends of the blade. But the interesting part is on top, where I only plot those elements that have a logarithm of larger than 8. Okay? So those elements are really thin. So anybody who has meshed in 3D with tetrahedra knows that it's nearly impossible to avoid having slivers or very bad aspect ratio elements in your mesh. If we were to use, so these are called slivers, and these are the elements that we are looking at here. If we were to use a synchronous algorithm, the same time step everywhere, these elements will be the ones that will slow you down by a factor of 6. Okay? So by using different time steps everywhere, these elements advance gracefully at their own pace, and we do the computation instead of in 1 year, in 2 months. Okay? So as I said, the energy is perfectly preserved. So this is the total energy as a function of the number of revolutions for the rigid case and for the soft case. And notice that here we have done 235 million of updates in the smallest element in this mesh. So we've gone, I assume, supposedly long enough to see some decay in the energy. So this is surprising, but not too much, because from backward error analysis, you know that the symplectic algorithm with a constant time step will preserve the energy for exponentially long times. There's no such an algorithm, such a theorem for asynchronous algorithms for multiple time stepping algorithms, but it seems to hold. And that's the case in every example I run, or we run. We also prove the convergence of these algorithms, and here, for instance, that is for an example, the plot of the L2 norm error the L2 norm of the displacement error as a function of the computational cost, both by using asynchronous integration or asynchronous integration. Okay, the same problem. So this is the synchronous curve. This is the AVR curve. So if you, for a given computational cost, you save. You get a more accurate solution using asynchronous integrators. So that means that you can actually use longer time steps and still get an accurate solution. You don't lose accuracy because you just take a longer time step somewhere. Well, yes.
So this was for explicit.
Yeah, oh yeah, explicit.
So the alternative might be to do implicit.
Yes.
Which may be computationally sort of more expensive, but let's just consider it for a moment.
Yeah.
How would these things play out? I mean, does that make sense? Or?
It does make sense, and you have like a continuum of methods of how implicit you would like to be. In the sense that you can solve the entire space-time region at once. You can solve 1 millisecond, 1 second. You see, you just choose a space-time region that you want to solve implicitly, and you have to solve for all the elements at the same time, essentially. So this is how the algorithm works. This is really the mechanism of how you do it. And this is very simple. This is done with a one-dimensional elastic bar, where you have 3 elements and 4 nodes. So this is, for all practical purposes, if you don't know finite elements, this is just a mass spring system where the springs are nonlinear. Okay? So as always, if you want to solve an initial value problem, you're given the initial positions and the initial velocities of your degrees of freedom, and you assign now a time step possibly different for each element in your mesh. You choose, for instance, the one that has the smallest time step, let's say the one in the middle. You take the 2 nodes and you advance them following piecewise linear trajectories with the velocity that you were given until you reach the desired the time step of that element. At that point, you have deformed your element. So you have pulled from the string, and there will be forces that will try to restore the spring to its natural position. And so what you do is you use those forces, and with those forces, you kick the masses. It's like hitting them with a hammer, and they will automatically change the velocities of the masses. It's like a ball in contact with a wall. It reaches the wall, and it changes the sign of the velocity right away. Okay? So after this step, you'll have 2 new velocities in your 2 nodes. Okay? Then you take the element that comes next. Let's say this one. So you go with the 2 nodes of that element, so one that is already here and one that is already here, and you go to do the time step of that element. Again, you repeat the same thing. Now you have a deformed configuration of your element. This is like a nonlinear elastic spring. You compute the forces, you hit the nodes, you change the velocity, and you proceed. It's simple as that. But the beauty of this is that this has a variational formulation. Okay? This arises from a variational principle. And so let me tell you a little bit about that. This is a review of Lagrangian mechanics. Okay? Again, we have our body that in the reference configuration, and we describe its motion with a deformation mapping. But now the deformation mapping depends on time. So for each time, we have a different mapping of each point here into a new point. So you define then the Lagrangian density as a function of, I'm missing one part here, but the function of the deformation mapping, the velocity, and the spatial gradient of the deformation mapping. And this is just going to be equal to the kinetic energy minus the potential energy of the material. So then you define the action, which is just the integral over the space-time region in which you are interested to solve of the Lagrangian density. And your physical trajectory will be the one, given by Hamilton's principle, that says that will be the one that renders this action stationary with respect to admissible variations. 3 steps. And this is the same formulation for a bunch of physical theories, electromagnetism, fluids, general relativity, etc. So how do we do this variation approach in discrete cases? So now with regard our, this is an example with our 3-element bar. Okay, so this is the bar, this is space, this is time. So assume that this is the trajectory of the bar. Okay, so this is the time step each element has done. And to each one of these space-time regions that we have here, we assign what we call a discrete Lagrangian. And that discrete Lagrangian is just an approximation of the action of the system in that space-time region. Then, since we want to have the integral of the Lagrangian density everywhere, we just have to add all these discrete Lagrangians to construct the discrete action sum. And then we use a discrete variational principle, discrete Hamilton's principle, that says that the discrete motion should render the discrete action sum stationary with respect to admissible variations of the nodal trajectories. That means just that you take the action sum, you compute its derivative with respect to the position of node A at time E or at time I, and that should be equal to 0 for every admissible variation. This is the discrete Euler-Lagrange equation, and this defines your algorithm. Okay? This exactly gives you the algorithm I described with masses and springs before. Exactly. If you choose the right discrete Lagrangian. Okay, so as I said, there is another theorem, there is a discrete Noether theorem that guarantees you that by construction you're going to have very nice properties. Some quantities will be preserved. And this is a flavor or a taste, this is just a taste of how you prove that. So consider again our evolution for the discrete system, but now we're going to focus on the evolution of the system from the red line to the blue line. Okay? And we're going to construct the action sum that contains all these space-time regions between the two configurations. So one observation that one immediately does is that if I take this mesh and I just move it in space, I just displace it in this direction, the action sum will not change. Okay? That means that if you add to each coordinate, to each nodal position in this small space-time region, a constant vector, you are going to get the same value for the action sum that you had at the beginning. So now you can take the derivative of this with respect to v, because this holds for every v. So we do that, and what you get is that the sum of all the derivatives of the discrete action sum with respect to all nodal positions in that space-time region should be equal to 0. But remember that many of these terms are just the discrete Euler-Lagrange equations of your system, the ones that define your algorithm. So they drop. In particular, the ones that drop are the ones in black. So in the end, what you are left with, after rearranging, is with the sum over red equal to the sum over blue. So this sum over blue defines what the total linear momentum, the discrete linear momentum of your system is. And this statement is the one that says that the linear momentum that you have at the beginning is equal to the one that you have later on in blue, for any blue configuration. Okay? And if you do the same thing with rotations instead of rigid body translations, you'll get the discrete angular momentum being preserved. So this is Noether theorem. Finally, I'm going to talk about two more things. I'm going to talk about choosing time steps arbitrarily, that will be time adaptation in space, and also about the parallel extension. So these two things come next. So the first thing I want to show is how I want to show a problem in which somehow it's necessary to choose different time steps in space as you progress in the simulation. Okay? So the problem we chose was a canister, a metallic canister, or let's say a polymer canister, because it's really soft, with a high explosive inside. And we hit it really hard from this side. The high explosive will start detonating, a shock wave will advance inside the canister, and it will deform the canister a lot. Okay? So just at the place where the where the detonation is occurring, you have a chemical reaction. You would like to take smaller time steps, much smaller, maybe 1,000 smaller, 1,000 times smaller. So we do that, and we adaptively change the time step to always take a very small time step on the detonation front. So, well, this is the movie, which is kind of nice to see. These are pressure contours. So red is very high pressure, and you see the two waves, one wave inside the